So quick review of the video that you watched that is up at the top. So if you watch that video, you could fill in these notes. Area under a curve is really the area bounded by the curve and the x-axis. So the area under the curve here is yellow. Here it's under the curve, even though it's above, because it's what's between the x-axis and the curve. And we saw in the video that any area that is above the x-axis, so this yellow one would be positive, this blue one would be negative, and in the third example, the green area would be positive, and the purple areas would be negative. So we did this really simple example, which you already knew the answer to. If you traveled 60 miles per hour for 4 hours, you would have gone 240 miles. However, you could actually do it as accumulation of change by figuring out the area under the curve if you graph the rate of change and the time. And your units will always be the two units multiplied by each other. So here the hours would cancel out, and you just get miles. If the shapes are nice, we can figure out the area under the curve using formulas that we already know. Usually rectangles, triangles, and this one, a semicircle. And then you could add up that area and figure the total amount, in this case, of water that's leaked out of the tank after 9 minutes. Again, here we have a particle moving along the x-axis. The yellow part and the red part, those two parts would be positive. The blue, the purple, and the green are negative. And so when we add it all up, we get negative 40. Based on the question, since this is moving along the x-axis, the negative 40 means that it's moved 40 meters to the left. But we're not only going to get nice shapes. In calculus, we're going to be able to figure out area under a curve even when the shapes aren't nice. But we're going to start with nice shapes. So here's the area problem. We've got some function, and it isn't a nice shape. It's not something you're like, ooh, I recognize shape A as a, well, it's not a rectangle. It's not a circle. It's not any shape that we would call it. It's like, oh, it's close to a trapezoid, but it's not. So how do we figure out the area if the shape isn't nice? And so the idea is, well, let's get an estimate. What would be a good estimate? Well, I could make a bunch of rectangles. Okay? So if we added, in this case, it looks like 1, 2, 3, 4, 5 rectangles. Would that be a good estimate? It wouldn't be too bad. Actually, oh, this rectangle looks really good. This one second from the right is definitely an underestimate, but we overestimate later on. So it's like, yeah, that might actually be pretty good as an estimate. So we're going to find that we can find this area either using lower sums, which are called inscribed rectangles. So what that means is in any interval, like this would be an example of an inscribed rectangle, this green one right here. Because we took the two values, we looked at this value on the curve and this value on the curve, and we used the smaller one and made a rectangle. If you always use the lower ones, does it make sense that your estimate would be too small? And then there's a possibility where you use the upper sums. Circumscribed rectangles like this one. Here's my 2 points, but if I use the top one to make my rectangle, that would be a circumscribed rectangle, and if I used only my upper sums, then my area would be an overestimate. And what we're going to find is that this approximation, we're going to use calculus, and the more rectangles we use, better our approximation would be. Because if they were smaller rectangles, they'd be more accurate. And if we went infinitely small, we'd have to deal with limits, and we're going to find out that this works out perfectly to be integrals. But we're going to first get there through all the theory. But in the end, we're just going to find an integral and be able to calculate an area under a curve. So, starting off with rectangles, you know the area of a rectangle. Height times the width, or length times the width. So if we had a constant function, right, this is really nice because the height would stay constant all the way along. Then the area is just this height, and the length between A and B would just be B minus A. No problem there. And if you had a nice graph with 3 horizontal lines, well, then it would be obvious that you should make those 3 rectangles and add them up. And then you'd have it perfect. Now, if you had a straight line on an angle like this, you probably could figure out a way to get the area perfectly, like we did in the video to begin with, right? You could make a rectangle and a triangle. Those are both shapes that you're able to figure out the area from. You'd be able to find this area exact with just 2 shapes. But if we look at the inscribed rectangle and the circumscribed rectangle, we could say if I use the lower point at 2, 4, my length is 2, my height is 4, the area of that lower rectangle would be 8. And if I use the larger rectangle, I'd have 5 times 2, and the area would be 10. And those would both be estimates, and we would know one is an overestimate, one is an underestimate. We know that the area is somewhere between 8 and 10. And because this one's a perfect straight line, you can probably see that it works out perfectly to be 9, but that's not always the case. If you wanted your approximations to be even closer, were you not done there? Do you need me to go back? No, good? Okay. If you wanted to get even more accurate, if we did 2 rectangles and calculated each of those closely, now my lower area is 8.5. Before it was 8. And my upper area, before was 10, but now that I make 2 rectangles, it's 9.5. And now I know the area is between 8.5 and 9.5. I shouldn't have given away that I knew the answer was 9. I should be like, oh, I'm feeling like I'm getting closer to the actual answer. So next we could do 3 rectangles and get closer, and 4 rectangles and get closer. So as we increase how many rectangles we use, the area improves. And of course, we already figured this out, that the actual area, if you broke it up into a triangle and a rectangle, we could figure out that it's 9. So the idea is, if we increase the number of rectangles, both for upper and lower, then it gets closer and closer to the real value. So here's some notation. If we went from A to B, and we broke it up into n equal sections, then each interval, or each section, would just be the total distance, right? B minus A is the total distance along the bottom, divided by how many sections you have, divided by A. Okay. We are also doing this for functions that are continuous, and right now, we're just thinking about things where the area is positive. We're not worrying about any of that area below the curve. So, what would we do? We would have to find out, if we were doing the lower sums, we would find out which was the lower point between x0 and x1, and that would be c1. And then we would multiply that by the change in x on the bottom, and that would be our first rectangle. And for the upper one, you would figure out which is the bigger value, and that would be the area of the first rectangle for your upper one. And you would go along and do that for all of your rectangles and add them up. Okay? The first mathematician that looked at area under the curve was Archimedes. Like when we talk about derivatives, we talk about Leibniz and Newton, and we're talking about late 1700s, early 1800s. When we're talking about area under the curve, mathematicians, Archimedes is like, I don't know, 300 BC, somewhere in that. This was happening way, way, way before derivatives. Archimedes called this method the method of exhaustion. If you're not accurate enough, do more rectangles. Oh. You want to get more accurate? Do 1,000 rectangles. Do rectangles until you're exhausted, because you keep doing more and more and more and more and more, and you can get more accurate. But you can never get there exactly, because you'd have to do an infinite amount of rectangles to get there. But you could, if you wanted to. You could just exhaust yourself and do more and more and more and more and more rectangles and feel like you got to the right answer. So what's going to be fascinating with integration is that you've got these two ideas separated by 2,000 years that come together. That's crazy. It's crazy that a major discovery 2,000 years earlier and another major discovery 2,000 years later, and they're like, these things are connected. That's crazy. Because I don't think those connections happen with other opposite things in math. Like, I don't think it took very long before someone realized that adding and subtracting were different. Wow, they're connected, right? That you figured out right away. So, the area is approximately the sum of all of these little rectangles, which we can write nicely with our sigma notation. So again, remember, sigma notation means to sum up a bunch of things. And we start with C1. So we start when I is 1. We keep going up to 1 until we get to the last one, which would be Cn. And these, the f of Ci, are all the different heights. And the change in x is always the same, because that's the bottom of each rectangle. And we made each rectangle exactly the same width. So we use a little c to represent the minimums. And we're going to use a capital C to represent the maximums. So if we add up all the minimums in the interval, that will get us the area under the curve, but be an underestimate. We will be guaranteed that we didn't add up enough. And then, if we do all the maximum points, we will get an overestimate. And we will guarantee that that area is too much. And then we'll be able to say that it's somewhere in between here and here. Which was really cool, because another thing that Archimedes did with his method of exhaustion is he was like one of the first mathematicians to really, really find pi. And he did it with this same idea. He got an underestimate for pi and an overestimate for pi. And he said, I'm pretty sure pi is between, well, I know that pi has to be between these two numbers. And if I want to get more accurate, I can go again and do it even more and even more. So his method of exhaustion was the first mathematician to get a bounding for pi. And this is like 300 BC. Really quite amazing. Of course, he probably cheated and was using a graphing calculator. Pretty certain. There's historical evidence. Okay. So the area under this curve, we are first going to find a very bad lower estimate. Okay, can you see those two rectangles? No, you can see one. There's this rectangle here. There's one here where we use this minimum C1, and it's at 0. So if we were adding up those two rectangles, the sum of two rectangles, in this case, since our value is from 0 to 10 and we have two rectangles, the bottom of each of our rectangles is 5. On the graph, you would have 0, 0. So your first C1 is going to be 0. And you have the point 5, 25. So your C2 is going to be 25. Again, you're using the minimum values of that rectangle. If you wanted, since each of them have a change of x, you could factor that out and bring it out in front of your sum. And so the change in x is 5, and f of 0 is 0, and f of 5 was 25. So we get 5 times 0 plus 25, and get an estimate for that area to be 125. Graphically, I hope you can see the 125. I hope you can see the green sections that we missed completely, and that our underestimate is off by quite a bit. So now we go, okay, well, let's do 5 little rectangles and see if we can get closer. So now each interval is 2. We add up the sums of all these rectangles. And again, for ease of calculations, we can pull out and factor out that change in x. And then, since it's all the lower values in each rectangle, we're going to be adding up 0, plus 4, plus 16, plus 36, plus 64. And we get 240. Which seems like a better estimate than 125. So I'd like you to try the 10 subintervals. And see what value you come up with. right, let's see how you did. $285. So apparently this is closer. You see how exhausting if I had a part D and I said, I'd now like you to try it with 1,000 something. Any guesses what the actual area is? We went from 125 bad estimate. We're at 285. You see all the little green spots still missing? Any guesses? 300. Good guess. Yeah, I like 300 because we're getting closer to something, and 300 is a nice number. Actually, mental math, about 333. No, I didn't do mental math and do 1,000 rectangles in my head. I cheated and used what we're going to learn later, okay? And just like, you remember when you did the definition of the derivative? And we learned a long way first to do something? We're going to do that for integration again. We're in the long way now, where we're adding up a bunch of rectangles, and then we'll come to this aha moment where we realize there's such a better way to do this, and we'll be able to do it much faster and much easier. But for right now, we're adding up rectangles. So, we're going to look at y equals x plus 1. So that's a straight line with a y-intercept of 1. We're going to think about the lower rectangles, and we're going to think about the upper rectangles. So that's why I've got it split in half there. And the graph there is to help you visualize what you have happening. So for our lower rectangles, those would be the ones where we always use the lower value of the rectangle. Each width of these is 1. And then you figure out f of 0, f of 1, f of 2, f of 3. And we get an area of 10. Now, when it's a straight line, this might seem really pointless to do upper and lower rectangles because you're like, I could actually use my triangle formula. I could figure this out exactly, Mr. JR, way quicker. What was Archimedes thinking? Well, yes. When it's a nice shape, we can figure things out quickly. But unfortunately, most of real-life examples end up with graphs that aren't nice shapes. Then we can do the upper sums as well and get 14. And when it's a nice straight line that averages out perfectly like this, I hope you can see that every underestimate is exactly equivalent to the overestimate. So the actual area will be 12. Does it make sense that taking the average of the lower estimate and the upper estimate is actually another really good estimate? And in this case, it works out perfectly. And the last example that we'll do today is looking at the area under a sine curve from 0 to 3. There's a picture of your sine curve. And approximately the rectangles you would use. This one looks like it got drawn a little bit too high. There we go. That would be the inscribed rectangle there. So the length of each of those, or the base of each of those rectangles, is going to be 0.5, 1/2. And we want to add up those sums. As 6, because we're adding up 6 rectangles. And again, we can factor out that change in x. And then we're going to have to plug in f of 0, f of 1/2, f of 1, f of 3/2, ooh. That one actually, f of 2, and f of 5/2. This should actually be, if we're using the lower rectangles based on the picture there, this one should be f of 2. This one should be f of 2.5, and this one should be f of 3. What I've done on this one is actually another method of estimating where you're like, it's annoying to always figure out which one's lower, so just use the one on the left and then say your estimate is pretty good. But then some of them will be above and some of them will be below, and you won't be able to for sure say my estimate is too small or too big. Now, for us personally, it doesn't really matter that we have some mathematical mistakes in these numbers, because the idea is still there. So I don't care if you skip this step and don't write it down and just put an approximation sign at the end. So that answer, probably because we didn't use f of 2, f of 2.5, and f of 3, would be a little bit off in the end. But that's okay. The idea is there. So again, if you're adding up all of the inscribed rectangles, all of the lower ones, this should be an underestimate for the area under the curve.